As part of the work of the Neocognition Laboratory, we'll share insights on the cognitive entanglement of artificial intelligence systems. There are two types of artificial intelligence systems. The first is symbolic artificial intelligence. Its principle is the synthetic encoding of human thought processes and content, knowledge, reasoning, logic, rules, physical laws, etc. It takes the form of a system whose internal workings are directly understood and controlled by humans. The second is empirical artificial intelligence. It functions through learning, supervised or unsupervised, from data. This learning process extracts synthetic categories of thought and relationships between these categories from the data. This form of AI corresponds to what is known as deep learning. Its fundamental units are formal neurons originally inspired by human neuromimetic models. Its internal workings are more complex for humans to comprehend. Hybrid artificial intelligence is a promising research avenue in artificial intelligence, aiming to overcome the respective limitations of both AI approaches. For symbolic AI, its lack of material grounding. For empirical AI, its lack of reliability, hallucinations, cognitive or cultural biases, excessive training costs, human, financial, energy-related, difficulties with specific tasks, and constant need for retraining. Neurosymbolic artificial intelligence seeks to leverage the unique advantages of each approach. For symbolic AI, adherence to formal frameworks, rigor, safeguards, interpretability, and ease of construction. And concerning empirical AI, real-world grounding. Our ability to interpret the synthetic categories of thought to which artificial neurons in a neural network respond may be a key element in combining the symbolic and empirical aspects of artificial intelligence. Accessing the semantics of neural synthetic concepts could enable true cognitive entanglement between the empirical and symbolic domains of hybrid artificial intelligence. A mapping, eventually autonomous and adaptive, of synthetic concepts within a neural network would make possible a connectivity, eventually dynamic, autonomous, and adaptive, between the respective semantic dimensions of empirical and symbolic AI. This would allow coactivity between them, mediated by an interfacing process, facilitating information transfer between empirical and symbolic modules. Such hybrid entanglement of empirical and symbolic AI modules would enable a continuous interaction between empirical and symbolic knowledge, allowing these two types of cognitive entities to nourish and even evolve each other. To achieve true neurosymbolic cognitive entanglement, we must clarify the nature of synthetic cognition that symbolic human cognition elements need to be aligned with. This understanding is essential to avoid the anthropocentric fallacy of assuming that artificial neurons' thought categories are analogous to human ones in terms of content and organization. The uniqueness of the thought categories in formal neurons arises from the gradual adjustment of their neural weights during neural network training. This deep learning process triggers a phenomenon similar to what Paul Watzlawick described as confusion in human thinking. An immediate search for meaning and connections, leading to a readiness to establish relationships, even where they might seem absurd to an external human observer. Search that may extend to include very fine details which might seem completely irrelevant to us. Faced with its initial confusion, an AI system introduces meaning by employing ingenuity to impose order on seemingly chaotic data. This explains why synthetic thought categories appear strange to us. Artificial cognition is, in part, fundamentally different from our own. Creating neurosymbolic cognitive entanglement between human knowledge and synthetic neural knowledge thus requires developing translation systems capable of converting human symbolic knowledge into informational content adapted to synthetic cognition categories. For example, this could involve reconstructing symbolic knowledge into semantic dimensions readable by a given neural layer. Neuroscientist Francisco Varela defines cognition as a structural coupling between a cognitive system, neural weights in the case of AI, and a system of external world characteristics to which it must coordinate, here, human semantics. This coupling gives rise to a world of meaning at the intersection of these two systems. The concept of coupling appears crucial for designing neurosymbolic cognitive entanglement, which should consist of hybrid synthetic human thought categories, where different semantic systems are articulated but converge locally. For example, using Vygotsky's approach, we could construct embeddings of symbolic knowledge, adapted locally to the vector space of the corresponding neural layer, that anchor theoretical symbolic knowledge, what Vygotsky called scientific concepts, into empirical categorical dimensions, what he called practical concepts, accessible to synthetic cognition. Conversely, such embeddings could also generalize and align synthetic thought categories encoded in formal neurons with human knowledge. A value added by neurosymbolic cognitive entanglement is that it could facilitate a series of improvements that cognitive neuroscience invites us to bring to our current artificial intelligence systems in order to evolve them towards qualitatively much more advanced general artificial intelligences beyond the sole approach of more data. Here are a few examples of these characteristics. 1. Modularity. 2. Connectivity, temporary or stable, between units and modules, and circularity. 3. Flexibility of contents, processes, and the structures that coordinate them, as well as the connections that link them. 4. Coordination of top-down and bottom-up processes. 5. Multimodality. 6. Metacognition. And finally, self-adaptive modification and autonomous evolutionary regulation of these contents, processes, structures, and connections. These neuromimetic characteristics can and must from the outset be conceived within a dual logic of neurosymbolic entanglement. Thank you for joining us on this exploration of cognitive entanglement in artificial intelligence systems. You can find the article mentioned in the video, as well as all the work from Neocognition Lab on neocognition.org. See you soon for a new video.